Okay? All right, here we go. And so the folks who came in after I took attendance, just see me after class, okay? All right, so the definition of a derivative is the slope of the tangent line. So the derivative of a function is taken at a point. So if this is your function, you take the derivative at that point. The slope of the line, the slope of the tangent line at that point is the derivative. That's the definition. All right? Now, let me go through some examples, or an example, and after I go through this example, we can talk more about this and make sure that it's clear. So in this case, the problem is we're going to drop a ball from a 1 meter height, and we want to determine the average velocity, the speed or the velocity at the impact, and the acceleration. So what do you think the average velocity, how would you go about determining the average velocity of that ball? You drop it, and how do you determine the average velocity? What do you think? Exactly. It's the distance divided by how long it takes to fall. So if you have a really accurate stopwatch and you let go of the ball, you know it's 1 meter high, and you can time it and it comes out to 0.452 seconds. So that's really easy to get the average velocity. What about the speed, the velocity at impact? So we know what the average is, and I'll show you the answer to that in a second, but how do you figure out? So what happens, before we get to that, when you first let go of that ball, in the very instant you let go of the ball, what's its speed? 0. And it speeds up, right, as it falls. Why is it speeding up as it falls? Gravity, acceleration due to gravity. So we can figure out the average velocity, but the average velocity is not the instantaneous velocity. And when it hits the floor, well, let's say the instant before it hits the floor, it's at that's its maximum velocity, because in the next instant it goes to 0. Right. Okay. So in order to figure out that speed, we can do a couple of things. The simple sort of algebraic method is a little bit simpler. And we can estimate the average, or estimate the speed. So we take a bunch of measurements. Instead of one measurement from the time of release to the time it hits the floor, take a bunch of measurements. Maybe you have a high-speed camera, so you can record that ball falling, and you know that exactly 1/10 of a second after you let go, it was 0.951 meters off the floor. And exactly 0.2 seconds after you released it, it's 0.804 meters off the floor. And it hits the floor at exactly 0.452 meters. So we could get the average velocity in each time interval, right? So in this time interval from 0 to 0.1 seconds, it dropped 1 minus 0.951, which is 0.049 meters. And you could get the average velocity there. You could take the average velocity in this interval, and this interval, and that interval, and that interval. And if you do that, here, we find that in this final interval, it's traveling at 4.13 meters per second. So that's certainly a better estimate than the average velocity, right? That's got to be closer to the truth. So we calculate the average velocity based on one time interval, time 0 and time 0.452. We can get a better estimate if we use smaller time intervals. In this case, 1/10 of a second, except for this last one. What if we used, instead of 1/10 of a second, we used 100th of a second? What's that going to do to our number down here? Is it going to be higher, lower, or the same? How many think it's going to be higher? How many think it's going to be lower? This final interval is going to be lower. Okay, all right. So let me clarify my statement. How many people think the absolute value of that number, will it be moving faster, slower, or the same speed if you have a smaller time interval? if we have a smaller time interval, so this last time interval might be, instead of 0.052 seconds, it might be 0.002 seconds. It is going to be moving faster because now you're looking at this thing falling for, instead of, in this case, this average is for 0.425 seconds. Right? This is the average for that time interval, and the average of that time interval is about 0.425. Well, if your time interval is 0.45, you're closer to the end. The ball has traveled faster, further, so it's going to be going faster because of gravity. So the more time intervals you have, that's going to approach the true final velocity, the true maximum velocity. I mean, at some point, if you have an infinite number of time intervals, you're going to reach the maximum. Can you shut your phone off, please? Yeah. So in this case, if we use these time intervals, we come up with a speed at impact of 4.13. But if we can get more data, we can get a better estimate. So I took those data points that were in the previous slide, and I plotted them in Excel, and you get a curve that looks like this. Right? So at time 0, the ball is at 1 meter. At time 0.452, the ball is at 0 meters. And we can plot a trend line through those data points and come up with an equation that describes that line. Right? You guys know how to use trend lines in Excel? What's that? All right, well, it's pretty straightforward, and I don't necessarily want to spend a lot of time on it, but really, if you plot data up, here's your time data, here's your Y data, you highlight all of that, you go to Insert, and you insert a chart, and you get something that looks like this. If you then click on the actual data points, you can add a trend line. And when you add that trend line, you can make it any kind of line you want. You can make it a linear, straight line, which wouldn't fit very well with that, right? I mean, it's clearly has some curvature. You can make it a logarithmic line. Would not fit very well. I can show it to you. Right? You can't make a log line because you have a 0 value. It doesn't like that. In this case, I plotted it as a, where's my trend lines? All right. Well, now I messed up my plot. I plotted it as a polynomial because that, in fact, gave me a perfect fit. And this set of data is perfectly defined by the formula y equals minus 4.891 t squared plus 1. So by using Excel, we can develop an equation that describes this line. Now, with that equation, at any time, we can plug in any time and get the distance or the height. So we can make this interval as small as we want. We could plug in a time of 0.200001 seconds. We could get any time interval we want. So you could go back to the data and determine these time intervals and get smaller and smaller intervals to try and get a better and better approximation of what the actual velocity is when the ball hits the ground. So we use this trend line, we get that equation. Instead of doing that, if we take the derivative, because we want to find, let me go back here, what we want to find is the velocity right there. The velocity is, by definition, the change in height with respect to time, right? It's the rate of change of position with respect to time. That's a derivative. The change in height with respect to time is the derivative of y. The slope of the line at that point is the derivative of this curve at that point. So if we take the derivative of this curve, of this equation, this expression, and plug in this time, we can find out the velocity. So this is why we use derivatives. We get a precise, exact answer. So by definition, the slope of the yt curve at any point is the change in y with respect to time, which is the velocity. So the change in y with respect to time, this is y. Y is equal to minus 4.891 t squared plus 1. So we substitute that equation for y and take the derivative of this. Now this is where you really need to go to your textbook or another source and find out what the rules for taking derivatives are. When you have an exponent, the rule is to multiply by the exponent and then reduce the exponent by 1. In this case, so here we have minus 4.891 t squared. So the derivative of that part of the function is 2 times minus 4.891 times t. The derivative of 1 is 0. And you can think about this as 1 times t raised to the power of 0. Because anything raised to the power of 0 is equal to 1. And if this is t raised to the power of 0, the derivative of that is 0 times 1 times t raised to the power of minus 1. Well, 0 times anything is 0. The other way you can think about that is t is not part of this. Is not part of this part of the function, and the derivative, it's a constant, and the derivative of a constant is 0. By definition, the derivative of a constant is 0. Does that make sense? For those of you who have not had any calculus, does that make sense?
A little bit. Is that because there's no curve?
We're going to take, you mean that the derivative of a constant is 0?
Yeah.
We're taking the derivative of y. How does y change with t? Right? We're going to take the derivative as it changes with t. That doesn't change with t. That's a constant. It never changes. And so the derivative of this, how does this change with t? It doesn't. So it's 0. All right? So that's one way to think about it, and it's conceptually correct. Another way to think about it is it's 1 times t raised to the power of 0. And if you follow the derivative rule, t to the power of 0, the derivative of that is 0 times t, which is 0. So mathematically it makes sense as well. Does that help? No? Who said no? Okay. Let me get back to you. What was you had your hand up. You were going to say something? I can try. Let's see. Let me find a piece of chalk that works. So, yeah, let me do this. Let me do this. Is that going to work? So, the derivative, oh man, I hate this screen. Let me do it this way. Like that. Okay. So, the derivative of any function raised to the power of n is equal to nx to the n minus 1. That's what the rule is. So if you have any function raised to the power of n, multiply by that exponent, and then reduce the exponent. So the derivative of x to the n plus c, and c is any constant, any number. is going to equal n times x to the n minus 1 plus 0. There's no value of x in here. So this is equivalent to x to the n plus c times x to the 0. And that goes to 0. Because we multiply by that exponent, we multiply by this exponent, and then reduce that exponent. And we end up with 0 times something, and it doesn't matter what something is, 0 times anything is 0. Play with a number.
Like a 3 or something.
Okay, so, well, let me go back to the, I forget exactly what the equation was. Let's say y is equal to 4.5 t squared plus 10, right? So the derivative of y with respect to t, take the derivative of this part. This is a constant, doesn't have to change. We're going to take t squared, multiply by that exponent, and then reduce the exponent by 1. And we have to multiply by 4.5 again, because that's always in there. Plus 10, and we can, it's a constant. So by definition, it's a constant. It goes to 0. It's 0. It's always 0. It's always 0.
So, for example, if you had 1.5 times 10 to the third, I would say third, would that be 3 times t?
No, because 10 to the third is a constant. So you have to take the derivative of a formula that has variables. So we're going to take the derivative of y, and this is y, and we're going to take it with respect to t. And so in this case, you've got a t. So if you tell me that y is equal to 4.5 times 10 cubed plus 10, the derivative of y with respect to t in this case is 0. Because there's no t here, and there's no t there.
But what if there was like 4.5 times t to the third?
Oh, yeah, yeah.
Yeah, would that be 3 times t squared times 4.5?
Exactly. Yeah. Okay. Does that make sense? Because you said you were... Okay. So if you're gonna take anything away from this last 2 minutes, take this away. Remember that. That's the general rule. And that's written in the back of your textbook, in one of the appendices of your book. There's a couple of pages of rules for differentiation and integration. All right. So I'm going to go back to the slides. So in this case, our function is y of t is equal to minus 4.891 t squared plus 1. And we take the derivative of that function with respect to t, the derivative of the function with respect to t, 2 times minus 4.891 is minus 9.782. Oh, it's over here. Minus 9.782 times t to the 2 minus 1, which is 1. And the constant is 0. So the derivative of that function is minus 9.782 times t. Now that we have the derivative, we can evaluate the derivative at the point of interest. So we want to find the velocity when t is equal to 0.452 seconds. That's when it hits the floor. So we simply plug this value of t into the equation here, and it comes out to minus 4.421 meters per second, which is significantly greater than the 4.13 that we originally estimated by looking at the time intervals. So it gives you a more precise, more accurate answer, and it's faster. This is much faster than trying to go through all of those averages and time intervals. And if you remember the rules, it's pretty straightforward. And if you don't remember the rules, you know, as I said, the back of your textbook is your friend. Use that. And I think, as I recall, you're allowed crib sheets on the exam, right? So go to the back of the book, write all those rules out on your crib sheet. They're really hard to remember unless you use them all the time. All right. So that's the derivative of y with respect to t. And the derivative of y, it's the change in y with respect to time, is the velocity. We can take the derivative of velocity. Right? We can just keep taking derivatives of equations. What's the change in velocity with respect to time? What do we know that as? Acceleration. So the change in position with respect to time is velocity. The change in velocity with respect to time is acceleration. So this describes acceleration in our example. So we can calculate the acceleration of that ball at any time. So the derivative of velocity with respect to time is the acceleration. And this terminology, symbology, simply says that we can look at this in time intervals. So we can take the change in velocity over some change in time interval. Like in our very first example, the time interval was 1/10 of a second. And we took the change in y every 1/10 of a second. Well, as delta t gets smaller and smaller and smaller, it approaches 0. And as that approaches 0, it approaches the derivative. So when that ball hits the ground at 0.452 seconds, 0.452 times 9.78, I'm sorry, take the derivative of 0.9782 times t to get the acceleration. The derivative of this is a constant times time, so time we multiply by the exponent, which is 1, and then reduce the exponent, which would then make it 9.782 times t raised to the power of 0, which is 1. And so the acceleration is minus 9.782 meters per second squared, which is the acceleration due to gravity. It's a constant. So using the derivatives, we can determine very readily position, velocity, and acceleration. Yes?
How do the units change with relation to derivatives? Does it go from meters per second to meters per second squared?
Right, because the velocity is in meters per second, and then we're dividing it by seconds. So meters per second gives us meters per second squared. No, this is the derivative of velocity with respect to time. So velocity has meters per second, and we're taking its derivative with respect to time. So the result is going to be meters per second, which is meters per second squared. Meters per second. And if you go back to the very beginning here, where's my first derivative? Here. The derivative of y with respect to time is the derivative of meters with respect to time, and we end up with a velocity in meters per second. So this derivative terminology doesn't change the units of the function. Okay. So not sure where I want to go with this. We don't really need to talk about this at this point. This is leading into dynamics, which I'm not going to talk about till next week. What it's saying is that the velocity at any time is equal to the initial velocity plus acceleration times time. And this would be S is this is velocity times time is position S. Velocity times time is meters. Acceleration times time squared is meters, so that'll give you your position at any time. And the velocity at any time minus the initial velocity, the square of the velocity at any time minus the initial velocity squared is equal to 2 times the acceleration times position. To be honest, I didn't really want to include these slides. They were given to me by another instructor. I'm not going to deal with this, but they're here, so I wanted to at least explain them. What I want to talk about is some more information about derivatives and why they're useful. So in this example, we've got somebody taking a ball and throwing it up in the air. So it's starting at let's see. It's starting at 0, wherever your height is, right? I'm going to throw it from here, and this is my 0. I'm going to throw it up in the air. How long does it take to reach its maximum height? How fast is it going at the maximum height? What is that maximum height? And I'll talk about the second derivative test of determining maximums and minimums. So again, why do we want to know about derivatives? Well, these are really hard answers to come up with if you don't use derivatives. I mean, if you throw a ball up in the air and this equation describes its elevation with time, what's going to be the maximum height? And how long is it going to take to get there? That's kind of difficult to do without derivatives. So let's use some derivatives to figure this out. This is the equation that we're given, 4.43 times time minus 4.905 times squared. That tells you how high the ball is at any given time. And if you take that curve and you plot it, or if you take that equation and plot it, you get a curve that looks like this. As time increases from 0, the value of y goes up and up and up until it reaches some maximum, and then as time continues, it comes back down. So let me go back to here. Because at low time, 4.43, if this is a really small time, is a larger number than this number. And so y is getting bigger. But at some point time, when time is very large, this value is bigger than this value. And so time begins to get smaller. And this makes sense. I mean, if you throw a ball up in the air, what's going to happen? It's going to go up and then it's going to come down. And so over time, it's going to rise up and then fall down. And it's going to reach some maximum point. So the definition of the derivative, the velocity at any given time is the slope of the tangent to that line. Right? So what's the velocity here? If y 0. Okay. What does that mean? Well, I don't think it's true to say acceleration is taken over, because acceleration at time 0 is the same as it is at time 5 seconds or 10 seconds. Right? Acceleration is constant.
Right, but it's the negative direction of velocity, positive, so it changes the sign of velocity.
Well, acceleration is always negative.
Right.
So it's negative here and it's negative there. So why do we know why do we know the velocity here is 0?
Because after a certain period, due to that function, the acceleration of the net amount of change on the velocity changes the sign from positive to negative.
I'm not sure if that's exactly right, and maybe I'm not sure you're exactly saying it right, but.
The ball stopped in the air and came down. They hit a point where it didn't.
So at some point, in order for the ball's going to come back down. If you throw it up with a velocity going that way, at some point, if the ball doesn't slow down and stop and come back down, it's never going to come back down, right? It's just going to go up into outer space somewhere. So the very fact that the ball has to come back means it's going up this direction. It's got to at some velocity. It has to hit zero so that it can then come back this way. It can't go up without going through zero to come back down. So conceptually and physically, that's kind of what's going on. But what does this graph tell you? If you knew nothing about this problem, how would you know that the velocity is zero at that point? Exactly. The slope of a line drawn through that curve at the maximum is zero, right? The slope over here is positive, and the slope over here is negative, and the slope right there is zero. Oops. So again, I've said this a couple times, the slope, the velocity at any time is the slope of the tangent line, and at its maximum, that tangent line has a slope of zero. So if you set the derivative, if you take dy dt and set it equal to zero, you can find out what the velocity is here, because we know that when that derivative equals zero, that's a maximum. I think. Maybe it is, maybe it isn't. I'll get to that later. Does this make sense so far? Yeah? And you're like,
This was not as bad as what we just went past. It's all just to me.
well, okay.
Don't worry, you continue on. I'll find help later.
Well, let me ask you this. Do you understand the concept that the slope of this tangent line is zero? Does that make sense? So the tangent line is a line drawn through a point at the curve, on the curve. And the slope over on this side of the curve is positive, right? So it's the rise over the run, and you've got an increase in height over some time period, so you have a positive slope. Over on this side, it's negative. Well, you can't go from positive to negative ever without going through zero, right? And if you look at this line, what's the rise? There's no rise, so it's zero over whatever time span it is. So by definition, that's a zero slope. And so any curve, any function whose first derivative is zero, marks a maximum. It could also mark a minimum, and we'll talk about how to tell the difference. Because this curve could be flipped over, and that could be a zero down here, and it's a minimum, not a maximum. So we're going to take the derivative of this function of y, set it equal to zero, and that's saying the derivative of y with respect to t, that derivative is the velocity, and we'll set the velocity equal to zero, and that will tell us where y max is. Or, I'm sorry, not y max, y max and t max. So the velocity is equal to the derivative of y with respect to t, and in this case, y was given as 4.43 t minus 4.905 t squared. The derivative of that is 1 times 4.43 minus 2 times 4.905 times t. So there's our derivative. And we know that at t max, the velocity is equal to 0. So we set this equation to 0 and solve for t, which is, in this case, 0.452 seconds. Once we know the time, where the maximum elevation occurs. We can put that time into the original function for y, for position, and solve for y max, which is 1 meter. Okay? Okay? Do you understand? Yeah. Okay.
So you put YT with, you put YT with, what's the other, well, oh, so what's the, so T max, oh, you put Y next to T, then you multiplied it, then you square, you put the, exponent next to it, so what?
Right, because the original equation for y was 4.43 times t minus 4.905 times t squared. Right?
Oh, okay.
So by taking the derivative of this equation, we found an expression for velocity. That's this. And at y max, we know velocity is equal to 0. So we take this expression for velocity, set it equal to 0, and find t. So this is the time when y max occurs is at 0.452. So now we know at what time. How do we know what the value of y is? Take that value of t and plug it back into the equation for y.
And then you get what's that, the speed?
This is y, the position or height.
Yeah.
Right, right. So we've got, in this example, we're talking about time, position, and velocity. And velocity is the derivative of position with respect to time. Okay. All right. So the question was, what were our original questions? What was our question? We have the time to reach maximum height. Just solved that. The velocity at maximum height we've already solved. That's 0. We just found the maximum height by plugging that 0.452 seconds into this equation. So the next thing to look at is whether or not this solution is in fact a maximum or a minimum. Because mathematically, it could be a minimum. Because a minimum will also have a 0 value for the velocity, the velocity. So if you just look at a generic curve, right? Here's a maximum, there's a minimum. In both cases, the derivative of y with respect to t is equal to 0. So the question is, with that, how do you know that you've got a maximum instead of a minimum? What's the difference between these two curves? So the time, okay, that's true. But if you don't know what the curve actually looks like, you won't necessarily know if the time you're dealing with is here or here. So you don't know where this curve is in the time space. But what do you notice about the curve? What's going on at a maximum? What's that curve doing?
Straighten up. Straight line.
It's rising up, it comes to a straight line, and then it falls, right? What's happening at the minimum?
It's coming out to a stop, and then it goes up.
It's falling, it reaches a 0, and then it goes back up. So it's the difference between a concave curve and a convex curve. So in one place, now think about the slope of what's going on here. For a maximum, what's the difference in the slope between here and here? Is this slope greater or less than the slope here? The slope here? You think the slope here is greater than the slope here?
No, because you got that 0 slope there.
Right, so in this case, for a maximum, the slope is approaching 0 and then becomes negative. At a minimum, when you're looking at a minimum on your curve, the slope is negative, approaches 0, and then becomes positive.
So that's a minimum, and that's maximum.
Exactly. So if the derivative is the tangent of the curve, it's the slope of the curve right? The tangent of a curve defines the slope at that point. So if the derivative of this curve is the slope of the curve at any point, if we plot the slope, if we plotted a curve, take the slope at this point, and the slope at that point, and the slope at that point, and the slope here, and 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 plot all of those points, we'd find that the slope, where's my eraser? I know it was in my hand. I don't know what to do with it. The slope right here is pretty high. It's fairly steep. So we'll plot slope and versus time. And we know the slope here is 0, right? And then the slope is negative. It gets more and more negative and then less and less negative. So the slope gets more and more negative, and then it reverses itself and starts to approach 0 again. So that right here, the slope is 0. And then it gets positive. So this is a plot of the slope of this curve.
And that's the symbolization for minimum.
Well, what it says is that's this point here, okay? And that is this point here. So we have 2 points with a 0 slope, and the difference between them is, what's this slope?
Negative.
That's negative, because the rise over the run, you're getting lower on your curve as you move along the x-axis. What's the slope over here? It's positive. So the way you tell the difference between a maximum and a minimum is take the second derivative. Take the derivative of the derivative. If it's negative, then you've reached a maximum, and if it's positive, you've reached a minimum.
So this is a maximum?
So the maximum has a negative slope for the second derivative. So therefore, in this case, this is going to be a maximum, and that's going to be a minimum. Okay? Does that make sense?
Thought the second derivative for that line would be 0.
For which line? For this? It is. And what I'm plotting is the second derivative of this curve. So at the maximum here, the second derivative of that curve is 0. Because I'm plotting the derivative of this curve. The derivative of this curve, what's going on here? It's the slope, and it's negative.
How about before that point?
Over here, it's positive.
That's negative.
No, this is positive. This is at time 0. And the change in this slope, what's going on? The slope here is much larger than it is right there, right? So as you go from this time to this time, the slope has to approach 0. And so that's what's going on here. The slope is getting less and less positive until you reach 0. And from here, it's getting more and more negative to this point. At that inflection point, then it becomes less and less negative until it reaches 0 here. So right in the middle there, that's the inflection point here. And then it becomes more and more positive again. Okay? Yes?
So, if you're taking the measurement at when the velocity is at 0, how do you know what the slope is? If the slope is going to be 0 at that point.
Well, the slope is 0 here.
Yeah.
Right.
How do you know, like, if you only find out the maximum, how can you tell from that equation?
All right. So let me move on to a couple slides, and I think I'll answer that question. I wanted to go through this so that you had a concept, a picture in your head of what's going on with the math. So let me do this. So what I just explained is that if the derivative of y with respect to t, if the derivative of position with respect to time is 0, and the second derivative is negative, the second derivative would be a negative slope here, then you've got concave down and it's a maximum.
Is that second derivative, is that taken from the same point, or are you taking another point in the slope and taking the derivative
Well, it'll be the second derivative of the equation.
of the same equation?
Right. So you take the, let me show you the equations. It'll become clearer. This is just sort of explaining the concept. So the derivative with respect to time is 0, and the second derivative is positive. This is what I was talking about over here. That means the curve is concave up, and you've reached a minimum. Okay? So let me show it to you this way. Yes? Oh. So the derivative of our equation for y was 4.43 minus 9.81t, right? Because our original equation, you come over here, the original equation was y is equal to 4.43t minus 4.409t squared. And we took the derivative of this, dy dt, became 4.43 minus 9.81t. And that's equal to the velocity, right? If we take the derivative of this equation, which is the derivative of velocity with respect to time, which is also the second derivative of y with respect to time. The derivative of this, that goes to 0, and then we have minus 9.81. And because the second derivative is negative, we know that it's a maximum at this point. Okay? So I think the thing to remember about this is, one, use the rules for determining the derivatives that are given in the textbook, in the appendices. Go to the back of that book. There's a couple of pages of that. The velocity is, by definition, the derivative of position with respect to time. It's the change in position with respect to time. The acceleration is the change in velocity with respect to time. The derivative is, by definition, the slope of the curve at the tangent point. And the second derivative is the same thing. The second derivative is simply the slope of the derivative at the tangent point. And the third derivative is the slope of the second derivative at the tangent point. You can take derivatives, the fourth and fifth and sixth and 10th derivative, if you really need to do that for some reason. And you don't often need to do that. Second, third, maybe fourth, but that's about all you're ever going to have to do. All right. So before I go on, I want to make sure that we're on board here. So, what do you think? What do you think? Does it make sense? Yeah. Okay. Questions?
No, I get it.
You get it? No, not you. Yeah, what's your name again? Jamie. Okay.
So if the second derivative is positive, that's your minimum?
Yep. Yeah. Which is it's kind of counterintuitive, but maybe that'll help you remember it. And if, and I'm not a big fan of memorizing things. I think it's way more important to understand what's going on. And in all honesty, if you've got an equation and you're not sure, and you get a number and you see the second derivative is minus some value, think about what that means. If the second derivative is negative, it means the slope of the first derivative is going from a high value to a low value. So the slope of the first derivative is going from a high value to a low value. Well, then the curve has to be rising rapidly at early times and then starting to level out. Yes?
If the second derivative is just a constant, does that mean there's only one curve?
Yeah. Whoops, let me come back here. In this case, I mean, you can't throw a ball up in the air and have it go up, stop, come down, and then go back up unless you take into account the floor, which changes things dramatically. So, by definition, that's the only curve you can have is a maximum. Well, in general, if the second derivative is a constant, yeah, because the second derivative is a constant. You can never get a minimum. If the second derivative is negative and it's a constant, that's all you have is one peak. If the second derivative was, if this were squared, cubed, this would be 2 times 2. This would be squared times something, I don't know, some constant. What is this? 3 times 4.409. And then this would be 2.443 minus 6 times 4.409 t. At this point, you've got to evaluate it at the time that you're interested in. All right, so if this is your second derivative, at time 1, you're going to have a negative value. At time equals 0, it's positive. So that would make it a minimum. You're going to have a minimum at time 0. Anytime, almost any time greater, certainly by the time you get to t equals 1, you've got 1 times 6 times 4, which makes this whole function negative, which would make anything after t a minimum. Okay, does that answer your question? Okay. What time is it? Let's see. Do you guys want to take 5 minutes, or did you want to keep going? All right. I'll give you 5 minutes, but I'm going to start in 5 minutes. Let's go get a drink, stretch your legs, or... No. No, it's either now or never.
Okay.
It's now or never.
Same thing I did for trigonometry.
David? David's not here? Corey? You're Corey? Okay. Uzo Amaka? Is that how you say your name?
No, just live.
Just okay. It actually says that here, but it has your other name first and then Liz.
Yeah. It's my grandma.
That's all right. You're probably one of the few people you've got a unique name.
Oh, yeah.
You don't sound like that's a great thing.
Oh, it's a great, I like it, I like it.
Who are we missing? Mechanics.
I was right the first time. Mechanics and materials.
Just like a car mechanic, only it's materials. All right, I don't know where Joshua is, but we're going to get started.
He fell in. He went to the bathroom.
Yes. Oh, I'm sorry, not... Who's... Jamie. I knew it began with a J. It's close. J-A-J-O, you know. 2 syllables. No, Joshua has 3, right? Joshua. Anyway. Excuse me? All right. So let's talk about some applications of this that have, in my opinion, more realistic meaning. So I said early on that I'm an environmental engineer, which is actually comes out of civil engineering. I'm not a structural engineer by any definition of that word. But one of the things structural engineers in particular really wanted to know is what's going to happen to that beam or that other material before they build that building, right? So when you think about, you guys probably weren't here last semester. Were you here last semester? Or your first term here? Second term, okay. Well, if you go back last year, I don't know if anyone was around here, if you visited or whatnot, but this building was under construction. And there were some problems with that building when it was under construction. And even now, if you go out to the, at Pollitt Walk on that side of the building, you can see that they've got what almost look like overhangs, right? So here's the side of the building, and they've got this like cantilever cover hanging out over the building. It's really important to know what that material is going to do before you build that building, right? You want to know how much that material is going to bend when it gets loaded up with snow or when the wind starts blowing. And derivatives becomes really helpful in figuring that out. Yes?
Can anyone recognize the irony of that?
Of?
The fact that the building had issues right next to the engineering building?
Well, not publicly. And in our defense, we had nothing to do with that building. That was completely private contractors, private consultants who designed it, private contractors who built it. We were not consulted. We would have done a much better job had we been consulted.
How political.
I am fond of my department, and I believe in my faculty. All right, so anyway, so in this case, this shows a beam sticking out of the side of a building, or it's somehow or another pinned on this pinned here, and that's what these hash marks look like. And you can put a load on this, and a load can be a point load, or it can be a distributed load, which is what we have here. And when you put that load on the beam, it's going to bend because there's nothing supporting this end. And we can talk about the deflection in the y direction. And as this beam deflects, it induces a slope on the beam. And you can just look at this figure and see that this slope changes. The slope of the deflection is 0 back here, and then it increases to some maximum value at the end of the beam. And we can use derivatives to figure out what that deflection is going to be and what the slope is going to be, as long as we can define the load. So a couple of definitions so that you have some concept of what I'm going to talk about. So we can look at the derivative. It's the rate of change of a parameter with respect to another. We can talk about the change in the slope with respect to position, the change in velocity with respect to time, the change in force with respect to position, the change in force with respect to time. All of these things we can talk about and analyze using derivatives. So in this case, we're going to define the y direction as deflection. And it's going to have units of inches or meters, depending on what system of units you're going to have. And we're going to define the slope of that beam as the derivative of deflection with respect to x. So previously we were talking about the change in position with respect to time, and that was velocity. Now we're going to talk about the change in position with respect to space, and that's slope. And in this case, it has units of radians. Okay, a couple of other definitions. And this is way beyond this class, and I don't want to get into a long discussion about what this stuff means, but I want to point out what they are and relate it back to why they're important to derivatives. So there's this thing called a moment. And you can sort of imagine if you've got a beam and you put a point load right here, what's going to happen? The beam is going to tend to curve, right? It's going to bend in the center, and then on the ends it's going to curve up. Well, that curvature is a moment. So this load on the beam pointing here causes the beam to want to curve upwards. And that's what the moment is. And it's a function of the change in slope, right? So if the slope doesn't change, there's no moment. The moment is 0. But if the slope is changing, there's a moment, and it's a function of how the slope changes in position. EI is simply, don't worry about what it is, it's flexural rigidity, and all it does is describe how rigid the beam is. And it's a function of both the material and the shape of that material. So,
It was called what?
flexural rigidity.
Oh, right.
So you can imagine, okay, back to mechanics of materials, right? This beam, if this were the beam and you put a load on it, that has a lot more flexural rigidity than this does. It's the same material, it's the same cross-sectional area, it's the same shape, but its orientation changes how strong it is. So that's all you really need to know about this. What's really important about this is the moment is by definition the change in slope, which means it's the second derivative of the change in position. Okay? So the change in position is the slope, and the change in slope is the second derivative of the change in position. Now this moment, this curvature, because you've got a load pushing down and you've got curvature pushing up, it induces what's known as a shear force, because within that beam, you've got one part of the beam being pushed down and another part being pushed up, and it wants to shear. And that shear is defined as the change in moment with respect to position. It's the derivative. But the derivative of the moment is the third derivative of position. So all I'm trying to show you here is that you can get all of these various parameters and describe how this beam is going to function by taking successive derivatives of position. The first derivative will tell you the slope of the beam. The second derivative will tell you the moment. The third derivative will tell you the shear force. And if you take the fourth derivative, it gives you that distributed load. So the change in shear force, right? You've got this beam. And as that shear force changes along the length of the beam, it's describing the force that's being applied to it. So the distributed load is the derivative of the shear force, which is the fourth derivative of position. So when I said earlier, you can take as many derivatives as you want. You don't often have to go beyond the fourth for any reason. But in this case, in this mechanics of materials, in this study of mechanics of materials, using those successive derivatives, we can describe what's going to happen to this beam when, for example, if you go out there and you look at those cantilevered coverings, what happens when you put 3 feet of snow on that? That has a lot of water weight. That's going to cause those things to bend. So you want to make sure that E times I is strong enough to resist that snow load. When the wind blows and it gets in underneath there and it pushes it up, you want to make sure that the flexural rigidity is strong enough to keep that from blowing away. It's why when you go to places like Florida, they've all got hurricane straps on their homes to keep the roof from blowing away, because that wind load will get in underneath the eaves and it'll lift that roof right off. So they put straps on to make that roof stronger. The new structural code requires them. Yeah, I'm sure there's a lot of old homes without it, but the new one does. All right. So these are just some definitions of how we can use derivatives in this mechanics of material. So just to summarize, slope is the change in position. The moment is the change in slope, which is the second derivative of position. The shear force is the change in moment, which is the third derivative of position. And the load is the change in shear force, which is the fourth derivative of position. So let me go through an example. You've got a cantilevered beam, and in this case it has a point load. All of the load is applied right to the very end of that beam. And the deflection due to that load is described by this equation. And this is just given to you. The manufacturer or another engineer might have developed this equation for you, and they give you this. And what it says is the position of the beam is equal to the force divided by a function of the rigidity times x cubed, and this is 3L times x squared. So L is the entire length of the beam, and this really describes where you are on the beam in relation to its entire length. Certainly the longer that beam is, a very long beam, is going to have much more tendency to sag. Yes?
So what I'm gathering is that a lot of these equations are already defined. We're not going to be finding any of them ourselves.
Certainly not in this class. No. As a structural engineer, you're going to revolve that. What's the word I'm looking for? You're going to figure that equation out. You're going to figure out how to define that equation as a structural engineer. If you're not going into civil engineering, you may never use an equation that looks like that. But in this class, you're just going to get it. I'm going to give it to you. Yeah, I mean, you're talking about structural analysis is at least it is a junior level course. So, yeah, we're not going to deal with that. So if this defines the deflection, we can find the deflection and the slope where x equals L. So by definition, we're given deflection, right? So we can simply plug in the value at x equals L, just plug it in. And this is just straight up old-fashioned algebra. When x equals L, we've got L cubed minus 3L times L squared, 3L cubed. That's pretty straightforward. And at L, then the total deflection is minus PL cubed over 3EI. That's what it is right there. So what's the slope of the beam at that point? Go back to your original equation. Take the derivative. Now remember I said the derivative of a constant is 0? Well, in this case, we have a constant times a parenthetical function. So you can do this a couple of ways. You can multiply this all out. You can take P over 6EI times x cubed minus P over 6EI times 3LX cubed, x squared. And then take the derivative of those two factors or components. Or you can simply take the derivative of this whole thing, knowing that as a constant, as a constant being multiplied by the parenthetical, it stays exactly the way it is. So this does not go to 0. The only time it goes to 0 if it's plus some constant or minus some constant. If it's a constant multiplied times a variable, you can't, the constant won't go to 0, the constant remains.
So it'd be P over 6EI x to the third minus P3. I don't know.
Well, if you multiply it out, it's going to be P over 6EI x cubed minus 3P over, how does that keep getting back there? 3P over 6EI times LX squared. Right? Now, what's the derivative of this? Well, this is this is the function of y. dy dx is the derivative of this with respect to x. So it's the derivative of that with respect to x. So we can take the derivative of this and then the derivative of that. So the derivative of this, what's the derivative of this? 3p over 6ei x squared. Well, yeah, 2 times 3p over 6ei times L times x.
Can you tell me again why you you put 2 times 3p?
So I'm taking the derivative of this. Do we need to leave? We're going to take the derivative of this with respect to x. So you multiply by the exponent and then reduce it.
But wouldn't you multiply it by the whole thing? Because you only multiply it by 3p. Aren't you supposed to multiply it by the whole thing?
No. So when you take a derivative like this, let me do this. The derivative of that is equal to the derivative of p over 6ei x cubed with respect to x minus the derivative of 3p over 6ei l x squared with respect to x. So the derivative of this is 3p over 6ei x squared, and the derivative of this is 2 times 3p over 6ei lx.
So it's not 2 times parentheses 3p over 6 e.
Well, it is. I mean, that's the same thing.
Well, it will not be the same thing because you're not multiplying by the bottom.
No, this is exactly the same. 2 times 3p over 6ei is the same as 2 times 3 times p over 6ei. Yeah.
I'm not seeing why it is the same.
Well, 2 times 3 is 6. 6p over 6ei. I mean, I don't understand.
Well, you have to do 2 times 6 ei too.
Where's 2 times? I don't see a 2 times 6.
No, so it's not going to be like, it's not going to be 6p over 12 ei?
No. No, because you're only multiplying by the when you multiply 2 times this fraction, you only multiply it times the denominator or the numerator.
Oh, it's 2.
Yeah.
You mentioned that the fourth derivative was the what force?
The shear force, the derivative of the shear force.
So that would be 0 here.
If I took the fourth derivative, well, this is the first derivative. The second derivative would be 2 times 3p over 6ei x minus 2 times 3p over 6ei. That's the second derivative. The third derivative is going to be 2 times 3p over 6ei. Oh, wait a second. Times L. That's times L. Lx. We take the second derivative. I'm getting ahead of myself. Let me get to I've got this in the slides. You're getting ahead of me, I should say. All right, so do we understand this derivative? I mean, you can certainly take some of these constants out for sure. Here? Right, so that becomes P over EI. Yep. And over here you've got P over 2 EI. Yeah. Yep. Other questions? All right. Let me go back to my slides because I think all those questions, the last couple anyway, are answered in the next couple slides. All right. So the slope, we're taking the derivative of this equation and we end up with P over 2EI times x squared minus 2LX, which is exactly this if you simplify it. All I did was take out P over 2EI from here and here, and you end up with x squared minus 2 times LX. So that's the first derivative. So that's the slope. Okay? We're on board here? All right. So the question was, what is the value of the slope at L? So you've got to plug in the value of L. So the value of the slope at L, P over 2EI, put L in for x, so it's L squared And remember, it was 2L times x, so now it's going to be 2L times L. And simplify that, and the slope of this beam is minus PL squared over 2EI. And again, this is something that is a pretty standard equation in structural analysis. I mean, you wouldn't necessarily go through this analysis every time you did a design because everybody knows that this defines the slope, but this is where it comes from, and that's why I wanted to show it to you. If you don't use derivatives, that's really difficult to figure out what that number is, what an equation is without using derivatives. If you use, you could come up with the average slope from here to here and the average from there to there and from there to there and all the way out. But then when the beam gets a little longer, what are you going to do? You got to start all over. In this case, it doesn't matter how long the beam is, the slope is going to be defined by that equation, always. Yes?
So wait, your substitute L for x.
Yes.
Well, wouldn't that make that L squared minus 2L squared? Or is it
L squared minus 2L squared, that's correct. And then you pull the 2 out, so you've got 2P over 2EI times, wait a minute, let's see, what am I doing here? L squared, L squared minus 2L squared is minus 1L squared. Yeah. So that's where the minus sign comes from. Yeah. Other questions? This is the first derivative. Yeah. I was getting ahead of myself because what's your name in the back? Mike? Michael was asking some questions, and I got ahead of myself a little bit. So this is the first derivative. All right, so why? Because if you're a... Right, so what I'm going to... is if you're a structural engineer, knowing what the slope of the beam is out here is really important because this is the maximum slope. And for example, if this thing gets loaded up with snow, you've got two problems. One is the beam strong enough to hold that weight? The other problem is even if it's strong enough, is it strong enough not to bend and cause that snow to come flying off on someone's head? So knowing that maximum slope is really important from a design standpoint. Yeah. You know, if you're going to become a biomedical engineer, that might not be all that important, but maybe it is. There might be some applications. Biomedical? I'm not a biomedical engineer. You might, but I don't know. I don't know. Not every engineer will do that. An electrical engineer? Probably not. I don't think.
As someone who hopes to be a biomedical engineer, I think it's so important because, especially if you're doing things with like orthopedics and replacement limbs, you're going to have materials that take loads.
Okay. All right. All right. Other questions? All right. You know what? Let me just stop there. Oh, come on! I mean, were they this way? Were they this way with Dr. Bill Packham and Dr. City?
It was not me. It was not me. It wasn't.
You know, I guess I got to go to acting school and entertain people a little bit more. Yeah, I'll pick up here on next week because we're not meeting Wednesday, right? What do you guys do on Wednesdays?
A lab.
A lab, okay. So I'll see you a week from today, and we'll pick up here and either go back to dynamics or jump into integration. I'm not sure which way we're going to go. Let's see how far we get. So you've got my contact information. If you've got any questions, feel free to let me know. Yes? I did?
No, I said, could you?
Oh.